Welcome to AI Frontiers, where the latest breakthroughs in cryptography and cybersecurity are explored through the lens of cutting-edge research. This episode focuses on key advances presented in 15 recent papers within the computer science, cryptography, and security category, often known as cs.CR. The discussion will highlight major trends such as privacy-preserving computation, federated learning, and the transition towards post-quantum cryptography. Listeners will gain insights relevant to security professionals, technologists, and anyone interested in the evolving landscape of digital protection. By synthesizing these research contributions, this episode aims to provide both technical depth and accessible context for understanding the challenges and innovations shaping our interconnected world. To frame today's discussion, it is essential to understand the foundational concepts of cryptography and security, pillars of the cs.CR field. Cryptography serves as the backbone for safeguarding the confidentiality, authenticity, and integrity of digital data. It achieves this through mathematically grounded protocols designed to ensure that only authorized entities can access or modify sensitive information. On the other hand, security encompasses a broader spectrum, focusing on protecting systems, networks, and infrastructure from an array of evolving threats. These disciplines are crucial for sectors such as finance, healthcare, government, and communications. The real-world impact of cryptography and security extends from the realm of abstract mathematical proofs to the global imperative of maintaining digital safety and trust in critical infrastructure. A central theme in current cybersecurity research is privacy-preserving computation within machine learning. As machine learning systems increasingly require vast amounts of data, maintaining privacy becomes both an ethical responsibility and a technical challenge. Recent advances, such as enhancing noisy functional encryption, have enabled computations directly on encrypted datasets, ensuring that sensitive information remains undisclosed throughout analytical processes. Additionally, solutions like homomorphic support vector machines, as demonstrated by first author and colleagues, allow secure financial decisions to be made without exposing confidential data during inference. These developments collectively underscore the importance of enabling robust machine learning while guaranteeing the confidentiality of individual data points during analysis. Federated and distributed security mechanisms represent another dominant trend in modern cybersecurity. With data and computation now distributed across numerous devices, organizations, and even continents, collaborative security frameworks have become vital. For example, self-supervised federated GNSS spoofing detection by first author and collaborators decentralizes the detection of satellite signal spoofing, reducing reliance on centralized data pools. The Beskar framework, introduced by Zhang and colleagues, exemplifies federated learning systems that incorporate both post-quantum security and differential privacy, ensuring that collaborative machine learning remains resilient and confidential. Distributed approaches such as these are designed to balance the demands of collaboration, privacy, and operational resilience in increasingly complex digital environments. The third major theme centers on cryptanalysis, the mitigation of quantum threats, and the security of AI agents. Ongoing cryptanalysis, as conducted by Lage and fellow researchers, continues to expose flaws in protocols that were previously considered trustworthy. The development of post-quantum migration strategies by first author and collaborators ensures that digital security remains robust in the face of advances in quantum computing. At the same time, the security of artificial intelligence agents is being scrutinized through efforts like agent exploit and LLM watermarking, which address emerging attack surfaces such as prompt injection and content attribution. This persistent, vigilant review is recognized as essential, given the ever-evolving nature of technological threats and the expanding attack landscape. The collective findings across these 15 papers reveal significant progress and impact within the cryptography and security domain, Aggarwal and colleagues have established optimal bounds for leakage-resilient algebraic manipulation detection codes, setting new benchmarks for secure message authentication. Lage's work demonstrates a practical attack that breaks lattice-based private information retrieval schemes for any database size, challenging previous assumptions about their security. Zhang and collaborators present Beskar, a framework that achieves post-quantum secure and efficient federated learning. Additional contributions include advances in red teaming and watermarking techniques for enhancing AI agent security. These developments reflect the integration of privacy, quantum resilience, and real-world applicability, marking a pivotal step forward for both research and practice. Several sophisticated methodologies underpin the advancements presented across these research papers. Differential privacy is prominently utilized, introducing mathematically calibrated noise to datasets or computations to protect individual privacy during analysis. Functional and homomorphic encryption techniques enable computations to be performed directly on encrypted data, maintaining confidentiality throughout the process. Federated learning allows model training to occur without the need to share raw data between participants, further safeguarding privacy. The adoption of attack taxonomies and automated red teaming proactively uncovers vulnerabilities, while data-driven frameworks assist organizations in planning and executing migrations to post-quantum security protocols. Together, these techniques are shaping the future of both privacy protection and system defense. The technical spotlight falls on differential privacy and homomorphic encryption, two methodologies that are fundamental to balancing security and utility in modern computational systems. Differential privacy ensures that the results of data analysis do not compromise the privacy of individual data points, thereby providing strong theoretical guarantees for personal privacy. Homomorphic encryption, by contrast, enables computations to be performed on encrypted data without requiring decryption at any stage, thus allowing sensitive data to remain protected during processing. Both techniques are central to privacy-preserving computation in contemporary machine learning systems. Their practical relevance is evident in sectors such as finance, healthcare, and federated learning, where secure data analysis is paramount. The first paper selected for detailed discussion is Leakage-Resilient Algebraic Manipulation Detection Codes with Optimal Parameters by Aggarwal and colleagues. This work rigorously quantifies the trade-offs between efficiency and information leakage in the design of keyless message authentication protocols. Optimal bounds are provided for secure algebraic manipulation detection, AMD, code construction, defining the maximum rates of information leakage permissible without compromising security. The authors present explicit code constructions that match these theoretical limits, ensuring both practical deployment and provable security. This contribution sets new standards for protocol designers, offering a definitive framework for constructing robust message authentication systems in environments where some degree of information leakage is unavoidable. The second highlighted paper, Cryptanalysis of a Lattice-based PIR Scheme for Arbitrary Database Sizes by Lage and collaborators, demonstrates the critical importance of continuous scrutiny in cryptographic research. This work introduces an efficient two-stage attack that compromises the privacy guarantees of a well-known lattice-based private information retrieval (PIR) scheme, regardless of database size. The attack's feasibility across all database sizes upends prior security assumptions and emphasizes the necessity for persistent cryptanalysis and protocol updates. This research underscores the broader lesson that even widely trusted cryptographic schemes require ongoing evaluation and adaptation in response to emerging analytical techniques. The third selected paper is Efficient Full-Stack Private Federated Deep Learning with Post-Quantum Security, authored by Zhang and colleagues, and introducing the Beskar framework. Beskar integrates post-quantum secure aggregation with advanced differential privacy, addressing the dual challenges of privacy and future-proof security in distributed machine learning environments. The framework achieves strong privacy guarantees and computational efficiency, and its evaluation demonstrates resilience against both classical and quantum attacks. This advancement paves the way for secure, scalable, and collaborative artificial intelligence systems, ensuring that federated learning can meet the stringent demands of post-quantum security while maintaining practical performance. Looking to the future, several directions are poised to shape the ongoing evolution of cryptography and security. Privacy-preserving computation is expected to become more practical and universally adopted, aided by advances in cryptographic primitives and hardware acceleration. Quantum-resilient protocols are moving towards standardization and will be increasingly integrated into operational systems. Automated red teaming and vulnerability discovery are anticipated to become standard practices within artificial intelligence and machine learning security workflows. Additionally, researchers and practitioners will dedicate greater attention to the human and organizational aspects of digital security, recognizing that technical solutions must be complemented by effective governance and user engagement. The synthesis and review process for this episode leveraged advanced artificial intelligence tools, including GPT 4.1 from OpenAI for content generation, as well as text-to-speech and image generation technologies provided by OpenAI. Human experts conducted comprehensive reviews of the synthesized content to ensure accuracy and clarity. Despite these efforts, potential oversights may exist, and listeners are encouraged to consult the original research references for detailed technical information. All cited papers are listed in the episode's reference materials to promote transparency and further exploration. Subscribe to AI Frontiers to continue receiving the most current research and insights in artificial intelligence, cryptography, and cybersecurity. This platform is dedicated to keeping you ahead of the curve through expert analysis and accessible explanations. Thank you for joining this exploration into the future of secure computing. In this podcast, we bring you the latest breakthroughs in computer science and AI straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights.